Hello students, welcome to Ma'am and Me Academy. I am your mathematics educator Bipul Babu, and today we are going to study decimal expansion of a rational number. This will be the last video of this chapter. I hope you have understood all the concept in this chapter very well. If you have any doubt, you can mail the doubt in the PDF format on our email ID. Okay, let us see what is there in decimal expansion of rational number. I have written some rational numbers here. Let us see the decimal expansion of these numbers. When the very first number is 17 divided by 2. When we will divide 17 by 2, you will get 2 8s are 16 and 0.5, right? And when we will divide 17 by 5, you will get 5 3s are 15 and 2 is remainder, 5 4s are 20. Okay. When you will divide 17 by 10, you will get 1.7, right? And let us divide 17 by 30. Let us divide 17 by 30. So this will be like this point, right? 30 6 are 180. Okay. So 13 5s are 150. The remainder will be 20, right? And we'll put a 0 here. You'll get 13 6 are 180. Then again the remainder is 20. That means this will go on repeating. You will get 0.5 6 6 6 6 so on. Okay. Now let us divide 17 by 3. Let us divide 17 by 3. You will get 3 5s are 15. The remainder is 2.0. 3 6 are 18, and it will keep on repeating itself, right? So you will get 5.66666 so on. Okay. Now why did I write so many examples of rational number? Let us try to understand whether we can derive any expression or any relation through which we can understand whether the given rational number is terminating or non-terminating. You see, here the decimal expansion is terminating. Terminating means it has ended, right? The division is ended here, terminating. And here it is terminating, so I am using T here. It is also terminated. Here it is repeating, right? So this is non-terminating. This is non-terminating and repeating. Non-terminating and repeating. Okay, you can see that 6 is repeating here, right? 6 is repeating itself. Here it is non-terminating, and repeating. Non-terminating and repeating. Now, if you see the denominator of each rational number, let us see the prime factorization of each of the denominator of the rational number. Now, in the very first question, the denominator was 2. Okay. So, prime factorization will be 2 only. Okay. Now, let us see the second question. Second was 5. I am writing the denominators here. Okay. We are trying to derive any relation so that we can tell without dividing. Let's see, I have divided here now. Without dividing, you can tell whether this expression is terminating or non-terminating. Okay, let us see how. 5 can be written as 5 only. Now in the third, the denominator is 10, which can be written as 2 into 5, right? And the fourth question, it can be written as, the denominator is 30, it can be written as 2 3s are 6 and 6 5s are 30, right? In the fifth question, the denominator is 3, so the prime factorization will be 3 only. Now if you can see here, the numbers, the denominators which had 2, 5 or 2 or 5 had the terminating decimal expansion. Let me repeat, the denominator which were having the prime factorization of 2, 5 or 2 or 5 both were terminating, right? Here it was the terminating decimal expansion. Here it was terminating decimal expansion. This was also terminating decimal expansion, and it was having non-terminating decimal expansion. This was also having non-terminating decimal expansion. Now what conclusion can we draw? We saw that for a rational number to be terminating decimal expansion, we need either 2 or 5 or both in the denominator, right? If you can see the fourth one, the prime factorization of 30 consists of 2 and 5, but it is not non-terminating. But it is not terminating. It is non-terminating. It is because of this extra person here, which is 3. So let us try to conclude this within a statement in the next screen. Okay. Now let us see what relation can we derive from those examples which we studied. The decimal expansion of a rational number will be terminating if the prime factorization of the denominator is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. This is the relation which we can derive from the examples which we studied. Let us see how. The first example was 17 by 2, right? 17 by 2. Here you saw the prime factorization of the denominator is of the form 2 to the power 1, right? So it is not of the form 2 to the power m into 5 to the power n, but we can write it so. We can modify this as 2 to the power 1 into 5 to the power 0. Okay, now it is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. It should not be negative here. Okay, in the second question, in the second rational number, it was 17 by 5, right? So here the prime factorization of the denominator was of the form 5 to the power 1. Okay, it is not of the form 2 to the power m into 5 to the power n. Let us make it as 2 to the power m into 5 to the power n. Here there is no 2, so we can write 2 to the power 0. So you saw that wherever the prime factorization of the denominator is of the form 2 to the power m into 5 to the power n, the decimal expansion was terminating. See, in the third question there was 17 by 10, right? In the third rational example, it was 17 by 10. The prime factorization of 10 is 2 into 5, right? The prime factorization of 10 is 2 into 5. So it is of the form 2 to the power m into 5 to the power n. Okay, so the decimal expansion of this number will be terminating. Now we had 17 by 30, 17 by 30, right? So that was 0.56666, right? Here the prime factorization of the denominator is 30 equals to 2 into 3 into 5, right? It is not of the form 2 to the power m into 5 to the power n, because there is an extra 3 here. Okay, there is an extra 3 here. If had it been 2 into 5, then the number would be terminating decimal expansion. But because of this 3, this rational number has the non-terminating decimal expansion. Now I think you have understood what was I am trying to say. I was trying to say that first find the prime factorization of the denominator of a rational number. If it is of the form 2 to the power m into 5 to the power n, then the terminating decimal expansion will be there. If it is not of the form 2 to the power m into 5 to the power n, then the decimal expansion will be non-terminating. I think you have understood a bit only, right? Let us make it more clear. We can see the exercise. The exercise is 1.4, right? Let us see the first question. For that, let me just rub it. Now let us see the very first question of exercise 1.4, which says, without actually performing the long division, state whether the following numbers will have terminating decimal expansion or a non-terminating repeating decimal expansion. See, we don't have to divide the numbers. Without dividing only, we have to tell whether the decimal expansion will be terminating or non-terminating. So let us see the very first part, which is 13 divided by 3125. We don't need to divide this number. For such questions, what do we have to do? We have to find the prime factorization of the denominator. So let us try to find the prime factorization of 3125. So let us divide it by 5. You will get 5 6 are 30 and 5 2s are 10 and 5. 5 125s are 625. 5 25s are 125. 5 times 5 is 25 and 5 ones are 5. So we can write that 3125 equals to 5 to the power 3 or 25, right? 3125 can be written as 5 to the power 5, and we can write this as 2 to the power 0 into 5 to the power 5, right? Can we write this 5 to the power 5 in the form of 2 to the power 0 into 5 to the power 5, because any number raised to the power 0 is 1 only, right? It doesn't make a difference. Now since this is of the form 2 to the power m into 5 to the power n, therefore the decimal expansion of this rational number will be terminating. So let us write it down. Since the prime factorization, you have to write in the similar way I am writing, okay? The prime factorization of the denominator is of the form 2 to the power m into 5 to the power n, okay? Therefore the decimal expansion of the rational number will be terminating. Okay, after doing 2-3 questions you will come to know, or you will understand the concept better. See, what did I do? Let me just repeat it for you. First we'll find the prime factorization of the denominator. We found the prime factorization of the denominator. It was 5 to the power 5. Now 5 to the power 5 can be written as 2 to the power 0 into 5 to the power 5, right? So this is of the form 2 to the power m into 5 to the power n. Since it is of the form 2 to the power m and 5 to the power n, so we can say that the decimal expansion will be what? Terminating. Now let us see the second part, which is 17 divided by 8. 17 divided by 8. Now I'll not write the theory part here, just we'll understand this. The prime factorization of 8 will be 2 to the power 3. It is very simple, right? 2 to the power 3, and it can be written as 2 to the power 3 into 5 to the power 0. Now you have made this in the form of 2 to the power m into 5 to the power n. So the decimal expansion of this rational number will be what? Terminating, right? Terminating. You have to write like this only, so I am not writing it for you. Okay, you can see in the PDF which you will get at Ma'am and Me Academy. Now let us see the third part, which is 64 divided by 455. Now let us try to find out the prime factorization of 455. 455 when divided by 5 will give you 5 9s are 45 and 5 1s are 5. You know this, 13 7s are 91. Okay, so the prime factorization of 455 is 5 into 13 into 7. Now you can see that this is not of the form 2 to the power m into 5 to the power n, because there are 13 and 7 extra. Okay, by this format I mean that there are no extra numbers other than 2 and 5. So here there is 13 and 7 as well. So we can say that the decimal expansion of such rational number will be non-terminating. What it will be? Non-terminating at repeating. Non-terminating but repeating. Okay, it will repeat. So how you'll write? You'll write like this: 455 is equals to 5 into 13 into 7. Okay, since the prime factorization of the denominator is not of the form, for this question you'll write not of the form 2 to the power m into 5 to the power n. Therefore the decimal expansion of the rational number will be non-terminating but repeating, right? Now let us see the fourth part, which is 15 divided by 1600. 15 divided by 1600. If when you will find the prime factorization of 1600, you will get what? 2 to the power 6 into 5 to the power 1. You can find it out like this, right? Now since it is of the form 2 to the power m into 5 to the power n, you can say that what? The terminating or non-terminating? The decimal expansion will be terminating. I hope now you have understood how to tell without dividing that this rational number will be having terminating or non-terminating decimal expansion. Now let us see the fifth part. For that I have to rub this. Okay, let me just clear it for you. And in the fifth part it is 29 divided by 343. It is 29 divided by 343. Meanwhile you can do it by yourself sideways. Okay, and if you get stuck in that, you can take help from the board. Fifth question is 29 divided by 343. 29 divided by 343. Now the prime factorization of 343 is 7 to the power 3. You can find it like this, right? 7 to the power 3. Since it is not of the form 2 to the power m into 5 to the power n, so the decimal expansion will be non-terminating, repeating, non-terminating and repeating, non-terminating and repeating. Okay, now let us see the sixth part, which is very simple because they have factorized it for you. The sixth part is 23 divided by 2 to the power 3, 5 to the power 2. Now you can see that the denominator is of the form 2 to the power m into 5 to the power n. So the decimal expansion will be terminating. Okay, the decimal expansion will be terminating. Now let us see the seventh part, which is very simple because they have factorized the denominator. 129 divided by 2 to the power 2, 5 to the power 7, 7 to the power 5. Now you can clearly see that it is not of the form 2 to the power m into 5 to the power n. Why? Because of this 7 extra, right? So you will write, since the prime factorization of the denominator is not of the form 2 to the power m into 5 to the power n, so the number will have non-terminating repeating decimal expansion, non-terminating and repeating decimal expansion. Now I think this is clear for you. Now you are understanding it very well, right? Let us proceed to eighth part, which is 6 divided by 15. Now for this part, you can see that this can be simplified. Whenever you get a rational number which can be simplified, first of all simplify it. Now you can see that this can be written as 3 2s are 6 and 3 5s are 15. Now if you see the prime factorization of the denominator, it is of the form 2 to the power m into 5 to the power n. How? We can write 5 as 2 to the power 0 into 5 to the power 1. So the decimal expansion of this number will be terminating. Now if you don't simplify it, what will happen? Let us see. If you don't simplify 6 upon 15, you will see the prime factorization of 15 as 3 into 5. Now you will compare it with 2 to the power m and 5 to the power n, and you will say that it is not of the form. So the terminating decimal expansion won't be there. There will be non-terminating repeating decimal expansion. But my dear student, you can see that this 3 will divide 6. Okay, so this 3 will be disappeared, or this 3 will disappear from this factorization. So 5 will be left only. And if 5 is there, we can write it as 2 to the power 0 into 5 to the power 1. That means the fraction or the rational number will have terminating decimal expansion. Okay, now let us see the ninth part, which is 35 upon 50. Now you can see that we can simplify it, right? So we will simplify it. 5 7s are 35 and 5 10s are 50. Now without dividing also we can tell that it is terminating decimal expansion because it will be 0.7, but we have to tell by this method. So the prime factorization of 10 is 2 into 5. It is clearly of the form 2 to the power m into 5 to the power n. So we can say the decimal expansion of this rational number will be terminating, right? And now let us see the 10th part, which is the last part. Let me just rub it here. Okay. 10th part is 77 divided by 210. 77 divided by 210. Okay. Now let us see. Can this be simplified? Yes, it can be simplified by dividing it by 7. 7 11s are 77 and 7 3s are 21 and 0. Okay. Now you see the prime factorization of 30 is 2 into 3, 6, 6 5s are 30. Since the prime factorization of the denominator is not of the form 2 to the power m into 5 to the power n, Therefore, the decimal expansion of this rational number will be non-terminating repeating. Okay, non-terminating and repeating. I hope you have understood all these questions. Okay, now let us summarize it once again. Okay. Now let us summarize what we have studied. We studied the decimal expansion of a rational number, right? Decimal expansion of rational number. Now, what was the rational number's decimal expansion? It was terminating. And on the other hand, it can be non-terminating as well. Non-terminating and repeating, right? Non-terminating and repeat. Now, for finding out the decimal expansion of a rational number without actually dividing, we can just focus on the denominator. You will find the prime factorization of denominator if it is of the form 2 to the power m and 5 to the power n. If it is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers, then you will say that the decimal expansion of the rational number will be terminating. Otherwise, you can say that the decimal expansion of the rational number will be non-terminating and repeating. I hope you have understood this much. Now, if somebody asks you that which number can have the decimal expansion as non-terminating and non-repeating, can you tell me non-repeating? Which number has the decimal expansion as non-terminating and non-repeating? Okay, this is irrational number. So you can make a note here. Irrational numbers have non-terminating and non-repeating decimal expansion. Non-terminating and non-repeating decimal expansion. Let me give you an example. 2.101, 001, 0001 and so on. Now you can see that this is not repeating because the number of zeros are increasing. Okay, the number of zeros are increasing. So you can say that irrational numbers have non-terminating and non-repeating type of decimal expansion, whereas the decimal expansion of rational number can be terminating or it can be non-terminating and repeating. Now let us see the second question, which says write down the decimal expansion of those rational numbers in question 1 above which have terminating decimal expansion. This I am giving you as a homework. What is there in this question? They are saying that you have to find the decimal expansion. We told them that it is terminating or non-terminating, but in this question you have to find the decimal expansion of the numbers from the first question which were having terminating decimal expansion. For example, in the ninth, I am taking the simplest one. Okay, in the ninth part, it was 35 divided by 50, which was 0.7, right? It can be simplified, no? 5 7s are 35 and 5 10s are 50, 0.7. That means they are asking you the decimal expansion of the rational number. Only those rational number which were having terminating decimal expansion. Okay, I hope you can do that. If you have any problem, you can mail the doubts in the PDF form on the email here. Okay, now the third question says the following real numbers have decimal expansion as given below. In each case, decide whether they are rational or not. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? The very first part is 43 point. This is the third question. Okay, for third question's first part is 43.1 2 3 4 5 6 7 8 9. Now they are asking, is it a rational number? Yes, it is a rational number because it can be written in the form of P upon Q. It will be 10 to the power 9, right? This is of the form P upon Q. Now they are asking, if it is a rational number, then what can you say about the prime factorization of Q? We can say that it is of the form 2 to the power m into 5 to the power n, right? You can see that this is formed by 2 into 5 to the power 9, right? Or you can write 2 to the power 9 into 5 to the power 9, right? 10 to the power 9 can be written as 2 into 5 to the power 9 whole power 9. then this power will be given to 2 and this power will be given to 5 as well. So you can write 2 to the power 9 into 5 to the power 9. So we can say that the prime factorization of q is of the form 2 to the power m into 5 to the power n. Now the second part is 0.1201, 12001, 001, 2 4 times 0, so on. Now after reading this number you will come to know that this is not a rational number, because each time the number 0 is increasing. Okay, the number of zeros are increasing here, so this is not a rational number. You can say that this is an irrational number. This is an irrational number, and since it is not a rational number, so we don't have to tell the prime factorization of q. Okay, now let us see the third part. Third part is 43.12345678 okay, and there is a bar over this number. Now this type of number you have seen in the 9th standard, where you converted this into p upon q form, right? Now this is a decimal expansion, right? This is a decimal expansion of a number. Now it is what type of a decimal expansion? It is non-terminating but repeating, Now since it is non-terminating but repeating decimal expansion, that means this is a rational number. This is a rational number. Now what can you tell me? What can you tell about the prime factorization of q? It is not of the form 2 to the power m into 5 to the power n. Why? Because had it been in the form of 2 to the power m into 5 to the power n, then the decimal expansion would have been terminating, right? Here the decimal expansion is non-terminating. That means the prime factorization of q is not of the form 2 to the power m into 5 to the power n. There would be any extra number here. I don't know what, but there would be any number. That is all for today. I'll see you in the next video with the new chapter, polynomials. Until then, if you have any doubt, you can mail the PDF format of your doubt on the email given here. And for one-to-one classes, you can join our courses at Ma'am and Me Academy.